in a way, that's quite a pretentious title for a 15-minute talk. So I apologize in advance for not being able to cover the entire field of video understanding. So I don't talk at all about subjective understanding, for example. I will only bias it to my own research agenda to some extent. So what have we been doing in video understanding? Basically, find the cat. Oh, we have no slides yet. Oh. Let me get back on that one. Yes. Basically, finding the cat. So that really has been an emphasis of the community for, well, I think for the last 15 years. So you may wonder, how on earth can you focus on such a trivial problem? A 2-year-old can do it effortlessly, right? Now, it turned out that up till the moment of deep learning and other advances, this was actually quite tough nut to crack. And why is that the case? Well, part of it is that although we do it effortlessly from a very young age, vision takes about 50% of our brain capacity. So most of the energy that we spend on a day is spent on vision, on looking and seeing and understanding and sensing our world. And this picture is very interesting. It's from a famous cognitive scientist, Van Essen, published in Science in 1992. And he basically laid down a blueprint of the functional decomposition of the human brain. And some of it was speculation, of course. But what he said was, well, there are all kinds of modules, and they are interconnecting with each other in forward and backward passes. The information is combined, and this very much resembles present-day deep learning architectures. Now, of course, we're all familiar with ImageNet and the impact that has made on the image annotation problem, image understanding. So here's a brief overview from slides I copied from Andrei Karpathy, showing basically the good performing systems, the architectures in this ImageNet competition. So in 2010, it was basically bag of words variants with smart encoding. So this is linear, local linear coding, but there were also feature vectors, color shift, soft assignment, and what have we. These type of approaches ended abruptly in 2012 when Alex Krzyzewski and his supervisors showed the world that deep learning is the way to go. So it was a great piece of work. And since then, everybody has been moving into deep learning, culminating in the Google net last year, which was, and also the Oxford or VGG net from Simon Jan and Zisserman, which were about equally good. Very deep networks. And note how this Google net resembles the architecture from Van Essen. So this is quite intriguing. So this is image understanding. How does that relate to video understanding? Well, you could say that video understanding very much is treated as image understanding, but then multiple images. So that is what the basic approach, what people have been doing in the literature. Of course, there are some adaptations to the particular problem of video, but very much the same architectures are also leading in video understanding. So there is also a yearly international competition in video understanding. This one is organized by the National Institute for Standards and Technology in the United States, so NIST, and the benchmark is called TrackFit. So NIST has been organizing benchmarks for a very long time, not only on video understanding, but also on face recognition, text retrieval, very famous, speech recognition, and machine translation, and so on. So back in 2000, they decided, well, there are all these people working on video understanding, everybody doing their own thing, working on their own data sets, reporting great results, but they are not really comparable. So they started their in an effort to promote video retrieval and video understanding research. So they do this by providing large and open data sets that everybody who applies for the benchmark can use. They define the tasks to execute on the data. And the nice part is you work on it during summer. Once the deadline is clear, you submit your results to NIST, and they will do the evaluation. And evaluation on video is cumbersome because you have to look through the video. There are lots of images to annotate, so they do a really good job there. And there is a yearly workshop, and the deal is that if you participate, you have to put all your cards on the table, so it's open innovation. So everybody who's doing really well in year X plus 1, everybody will have copied it and improved it further. So it's really fostering progress in that sense. And over the years, many teams from international universities and research labs have participated. So one of the tasks that has attracted a lot of attention is what's called the concept detection task. And here the goal is to find cats in short video clips, essentially. But also aircraft, beaches, and so on. There is a slight difference here with ImageNet. So the dataset is highly imbalanced. And also the objects are not necessarily picture perfectly framed, right? So the cat can appear anywhere in the video. That's a slight difference. So there is more visual variation, I would say. Nonetheless, the approaches that work in ImageNet also work really well in this TrackFit campaign. This is an overview of concept detection in video and the teams that have done well. So I focus on the teams I've been working on in the past year. So first with the University of Amsterdam. Sometimes we did well, sometimes not so much. And around the end of 2008, 2009, 2010, we had a really good approach using color shift and soft assignment, so really the traditional bag of words pipeline. We thought that was good enough to start a spin-off company that became UVision, and with UVision we did also quite well in this benchmark. I think here this is Tokyo Tech, also a very active team in this benchmark. And in 2015, UVision was acquired by the end of 2014. And Qualcomm is the best performer in the forthcoming edition that will be announced in November. So great. So you may say the performance varies a lot over the years. So what's going on? Is it getting harder? Is it getting easier? Or you don't really care? Or there's no improvement? Well, as it turns out, every year there is a new data set and the task changes. So the set of concepts changes, the data set, the video collection changes. So you cannot really compare editions over year. So we did an experiment with systems from 2006, 2009, and 2015 to see how well performance has increased. And we did this with the different systems on the same data sets. We did two variants, one where we have a training and test set that are similar in visual distribution, and one that is completely different. Now, as it turns out, from 2006 to 2009, so this is essentially the transition from very simple features to bag of words, and then all the fancy bells and whistles that you can invent there. So performance doubled from 0.2 mean average precision to 0.4 for the situation where the test set was similar in visual characteristic as a training set. When you train on the one set and test on a completely different video collection, performance drops, so that is this part of the bar. But here again, also for bag of words, the performance kind of doubled. And now this is with one of the layers in the Google net, so the 5B cat layer, if I'm not mistaken, and we see the same jump. So deep learning causes another jump, and this was already good enough for most clients in the business of the startup company. And well, I think this is good enough for practical use. So I will show you some results. And this is the same tactic that Matthew showed, basically. So Matthew showed concept scores over time in the video. We use the concepts to search in a large video archive. So this is 200 hours of video. And we search in it for a particular category, let's say airplane. I click it, and then you see the results. So this is a cross-browser. What does it mean? Is that this is the time axis of a video. So it found this particular clip in the video that is the most likely to create an aircraft. And this is the entire video where this fragment originates from. And this is the ranking. So this is most likely, less likely, etc. And we can traverse through the list. And you can see, well, that's actually pretty good. So this is searching in 200 hours of internet video archives, or the test set of TrackFit this year. Now, we can also do animals. Doesn't really matter. Changing the training set. So there's a dog here. So general category, animal. Easy to do. Babies. Easy. So notice that there are hardly any mistakes in the top 100. I remember times when we were happy when we had one good result in the top 10, and we said, "Oh wow, look at that! This is really getting somewhere." So this is quite amazing, actually. Now one more, like traffic situations. All easy to do. Now, this can also be done on a mobile device. So a short clip. So this recognizes concepts on the fly on a mobile device. So without connecting to the cloud, just using the system on the chip that is in the Qualcomm devices. So it takes a few milliseconds to recognize what's going on. And this is all deep learning. Okay, that was today. That's already available. Now, what brings tomorrow? Well, of course, I cannot predict the future, but the Internet of Things seems to be something that is here to stay for a while. So we have drones, cars that want to understand what's going on, IP cameras, even your microwave may want to understand what's inside. And all of it is really dependent on video understanding. So, of course, we can do video understanding with just the concepts, but I think for precise understanding of car situations or drones, we need spatiotemporal decomposition. So we really need to separate the what and the where in that regard. So really understand how the action or the object of interest is traversing over time. And we have done some work on generating such tubelets, as we call it. So this is the ground truth, the red tube, which we aim to achieve. Now, what we do is we perform a supervoxel segmentation on the video. It generates an over-segmentation of the video, and those supervoxels can be grouped. So we group them by several criteria, like similarity in color, texture, fill, size, and so on. And then you will get around those supervoxels, you can put a tube. So you get a set of tubes like this. So each of those blue things is a tube proposal that we propose. And you see the overlap, sometimes very bad, sometimes quite good. And by doing so, you reduce the search space of possible tubes in the video enormously. And you can encode them with deep learning. So rather than encoding the entire video, now you can encode tubes in the video. Now, as it happens, and this is basically continuing where Lior stopped, so image annotations can be used for action recognition. Indeed, we did an experiment with training all the ImageNet categories that have more than 50 examples. Turns out that there are about 15,000. And with a basic AlexNet, we found that objects make sense for actions. So the objects that matter for the action, playing cello, for example, are indeed cellist and violin cellist and so on. This is typing, and indeed object computer and keyboard pop out. And these action relationships, object action relationships, is generic. So you can use it for action recognition, using just the objects. This is a forthcoming ICCV paper where we basically translate objects to action so that we can do action recognition without the need of any video or action example. So you can imagine that for things like playing soccer, grass, and a ball and a goal are important objects. And we found a very simple way to achieve this. So we take a video, we encode it with the various object responses, and then we simply multiply it with an object action affinity value. And this object action affinity value is a cosine distance between two vectors that are obtained from word2vec. So Leo talked about this before. And this enables understanding of a video without using any video examples or action examples to train it. So this is pretty cool. And to show you some examples, and these are for the moment simple sports videos. So here green is the prediction and yellow is the ground truth, or yeah. So we predict the correct action label, and we also find the enclosing tube. Let me play another one. So this is another success. And here's a failure case. So this is playing golf, but we only find the stick and miss the entire thing. That already brings me to the conclusion. So I think video recognition technology, when it comes to concepts, is ready for use today. Spatiotemporal video understanding is coming very soon. And Qualcomm enables the on-device deep learning solutions to achieve this for the Internet of Things and so on. Thank you.
Thank you very much.